are discussing the very important topic which is related to the electronics, but it is a miniature device, that is the microelectromechanical system, that is nowadays is known as the MEMS. And these MEMS are used in every field of the electronic device and in every fabrication of the electronic circuit. So these MEMS, what is this what is this MEMS? These MEMS are the microelectromechanical system, and these are known as the MEMS, and these MEMS are very tiny devices that combine mechanical and the electrical component to detect and convert changes into the electrical information. So microelectromechanical system, that is the MEMS, is a device that combines mechanical, as the name suggests, mechanical and electrical components, and to detect and convert the changes into the electrical information. And they are used in a variety of modern devices. That is, nowadays we use the cell phones, we use the cameras and the pacemakers, we use these MEMS. Moreover, these MEMS are used also in the sensors. So what is this MEMS, or sometimes it is called a MST? If we talk about the United States, the technology is known as the microelectromechanical system, or the MEMS, or in Europe it is called the microsystems technology, that is the MST. So these are the similar technology, MEMS or MST, microsystem technology or microelectromechanical system. So what are these MEMS? Microelectromechanical system is the micro means small size, micro fabricated structures, electrical signal or control, mechanical functionality we use in this, and system, it is a device, structure, system control, that's why it is a MEMS. So micro means small size device we will prepare, electro which just we give the electrical signal, mechanical functionality done in these type of MEMS, and system, why it is called, because a device or a structure we are preparing by using this combination. So if we talk about the definition, you see on the right hand side there is a mini devices. So micro machining, micro fabrication, micro manufacturing, this all are related to this MEMS, and refers to the fabrication of the devices with at least some of their dimensions in the range of micrometer. So when we are preparing a device in the range of micrometer, then it is a MEMS. So MEMS is a technology of very small devices, and it is a combination of the mechanical function and the electrical function on the same chip using the micro fabrication technology. So a chip is prepared, that is a chip, we are having a chip, that is a MEMS, which is having a combination of the mechanical as well as the electrical function. MEMS are made up of the components between the 1 to 100 micrometers in the size. MEMS devices generally ranging size from the 20 micrometer to the millimeter. Nowadays we are also having a nanometers. So MEMS and microelectromechanical system is a technology, can be defined as the electromechanical and miniaturized mechanical elements that are manufactured using the micro fabrication techniques, and its physical dimensions can be varied from sub-micron level to the several millimeter. So MEMS device comprises of both moving and non-moving elements. Usually non-moving elements will have the simple structure and the moving elements may have the extremely complex structure. So MEMS has a interdisciplinary nature and uses the design, engineering and manufacturing knowledge from a wide range of technical area including IC fabrication technology, mechanical engineering, material science, electrical engineering, chemistry and the chemical engineering, and is a sub-technology field. MEMS has its unique application in the systems ranging across the medical, automobile, electrical communication, electronics and the defense applications. Currently, MEMS devices includes inkjet printer heads, airbag sensors, projection display chips, computer disk drive heads, pressure sensors, optical switches, biosensors, micro valves and the many products that are all manufactured and shipped commercially in the high volume. MEMS consist of the following component. Number 1 is a microsensor, second is the micro actuators, microelectronics and the microstructures, all combined and produces the MEMS. So, microstructure, microelectronics, microsensors and micro actuators. MEMS are also terms as the microsystems with classified as mechanic, electronic and optics, and electromechanical, optoelectronics and micro optoelectromechanics, that is MOEM. So, these are the microsystem. Now, the intrinsic characteristics of the MEMS are the reason for commercialization and the technology develops may vary by the application to be achieved. So, the three major merits of the MEMS devices and the microfabrication technology. What are they? Number 1 is the miniaturization, number 2 microelectronics integration, number 3 parallel fabrication. So, these three types of merits which makes it so important. Nowadays miniaturizations, like we are having a very small device where we can put the MEMS easily. Microelectronics integrations means we integrate the electronics with the mechanical formulation. Third is the parallel fabrication. A multiple fabrication of the MEMS are easily available. So, MEMS products will compete in the market for its unique advantages like fast speed, functional surety, size, compatibility and the lower cost. And there are some complex design challenges to achieve the above advantages from the fully functional and potential MEMS element. So, how these are important merits? If we talk about the miniaturization, the scale of MEMS usually in the range of the few microns to the centimeter. So, though the huge area of the MEMS devices may occupy much bigger volume. So, small footprint of the MEMS devices is with the operational advantages, smooth spring action, moreover high resonance, super sensitive and low thermal reach. For example, if we talk about the hard disk drivers in the computer has a writing reading speed in a few microseconds. So, MEMS device with the smaller size allowing the biomedical machines to be less intrusive. So, sensing probes we use the MEMS. In practical, smaller devices sizes has more devices per wafer, greater economy, and the miniaturization of the device generally scales favorably the cost of the MEMS and easily usable, and it is a portable, can be used in the small devices also. Another type of merit is the characterization is the microelectronic integration. As we talk about the, it is a microelectronic integration, means we can integrate this electronics with the mechanical function. So, circuit are used to produce the sensor signals, provide power and control, improve the signal qualities or interface with the control computer electronics. So, MEMS products today are increasingly being embedded with the computing, networking and the decision making capabilities. By integrating micromechanical devices with electronic circuitry and offering the combined system as a product. Significant advantages can be produced in the competitive market as it is very valuable as devices are rapidly miniaturized. So, and rapidly we require the more efficiency and we require the more integration. So, ability to seamlessly integrate mechanical sensors and actuators with the electronic processors and controllers at the single wafer level is one of the most unique characteristics of the MEMS. So, this process paradigm in referred to as monolithic integration, the fabrication of the various components on a single substrate in an unbroken wafer level process flow. And this word, if we talk about the monolithic, which is the one stone, means a one wafer we are having, and the one wafer we can have the we can get the integration of the electronic as well as the mechanical devices. So hence monolithic fabrications, that means that fabrication on the one piece of the wafer. Third point, which is also the one of the important characteristics, is the parallel fabrication with precision. MEMS technology can realize 2 or 3 dimensional features with small dimensions and precision that cannot be reproduced efficiently or profitably made with the traditional machining tool. So, combined with photolithography, MEMS technology can be used to realize unique three-dimensional features such as inverted pyramid cavities and high aspect ratio and through wafer holes, cantilevers and the membranes. So, to make these feature using traditional machining or manufacturing method is prohibitively difficult and inefficient. But the MEMS and microelectronics are also different from the traditional machining in that multiple copies of identical masking are made on a same wafer. Means we prepare a mask and that mask again and again used to create a multiple copies of the same device. So, MEMS and microelectronics are also different from the traditional machining as a multiple copies can be created on the same wafer with the different material. So, if we talk about the history of this MEMS in 1989, the Microelectromechanical System introduces at the workshop, that is the name of the micro tele-operated robotic workshop. After that, it is published in the IEEE catalog. Then the Professor Roger Ho, the University of the California, first announced the acronym of the MEMS. And this MEMS was explained by the Roger, and National Science Foundation funded a set of the MEMS project under the Emerging Technology Initiative, and this is really a emerging technology as it just changes all the scenario of the electronic devices. The Defense Advanced Projects was given, and the rate of filing the patent in MEMS was first in 1997. The most conservative market studies predict a world MEMS market and that produces a larger that in 2000 jump in 2003, and finally in the phrase MEMS has arrived. Now Nadim put that together one of the finest MEMS primers. Nowadays we use MEMS on the printing technology, and nowadays we prepare a MEMS by using the printing technology on a paper, and it is a use and throw type of electrodes we can produce on that, and we can design a MEMS, and the MEMS is also granted the patent by the United States at that time, and added many more illustration and pictures developed familiar with this technology. And nowadays this emergence of the wireless and the radio frequency as a new market of the MEMS technology. Nowadays we are using the wireless and the radio frequency, we use these MEMS. So how the MEMS made, how we can prepare these devices or these systems, and this fabrication we can get like just producing a very tiny device that is similar to the ant. So how we produce these devices, the tool found in a standard machine shop, and this tool must we use the mask and the replica we can produce at extremely high speed. Some of these machines are capable for producing the feature of the sub-millimeter range. It is called the micro milling and becoming a popular micro fabrication. And the first MEM and indeed the bulk MEM today are fabricated using the techniques borrowed and adopted from the integrated circuit fabrication and the semiconductor processing. So IC technologies or IC techniques create the structures on the thin flat substrate. Usually we use the silicon on that, and in the series of the layered processes we can fabricate the MEMS devices. The fabrication of the products deals with the making of the machine, structure of the process equipment by casting, forming, welding, machining and assembling. But this fabrication is classified into the two part. One is the macro and second is the micro. In the macro fabrication structures, part products that are measurable observed by the naked eye, that is the greater than that of the 1 mm in size. Then another type of the fabrication is the micro fabrication, which is the miniature structure parts products that are not visible with the naked eye, that in the size of the micron. So we cannot see that. So methods of the micro fabrication is the material deposition, material removal, that is also called the etching. So most of the times we prepare the micro fabrication. So in which first we deposit the material and another is the removal. Both we can do, like etching or the deposition. Manufacturing processes that can create extremely small machines have been developed in the recent years. Electrostatic, magnetic, electromagnetic, thermal actuators, motors, valves, gears, cantilevers, diaphragms and tweezers of the less than 100 micrometer size have been fabricated by using these technologies, and these have been used as a sensor for the pressure, temperature, mass flow, velocity, sound and the chemical composition, as actuators for linear and angular motions, and as simple components for complex systems such as lab on a chip, robots, micro heat engines and micro heat pumps. So device that have a characteristics length of less than 1 mm but more than 1 micron, that combine electrical and mechanical components, and that are fabricated by using the current manufacturing techniques. And these MEMS include surface silicon micromachining, bulk silicon micromachining, lithography, electrodeposition, plastic molding and electro discharge machining. These are the manufacturing techniques through which we can prepare the MEMS devices. Most of the time the lithography techniques are used, that is the photolithography, for the construction of the MEMS, making the small machines with the movable or controllable parts. MEMS are finding increased application in the variety of industrial and mechanical fields with a potential worldwide market. If we talk about the MEMS fabrication, we use the technique as we prepare the integrated circuit fabrication or the semiconductor processing. So, such techniques create texture on the thin flat substrates. Generally, we use the silicon, and in the series of the layered processes, it is constructed. Now, if we take an example, if we construct a MEMS pressure sensor, so it is a bulk micro machining. So, we start with a thin silicon substrate. You are seeing on the screen, it may be in the form of the square or in the form of the round shape, and it is called a wafer. That is a silicon wafer, that is a substrate typically measuring 200 to 400 micrometer thickness, and then a thin layer of the silicon dioxide is then grown on this wafer. You see silicon dioxide layer grown on this wafer. Next, what do we do? A thin layer of the photosensitive material, which is called the photoresist, which resists the light, or the simply resist, is deposited on the silicon dioxide layer in a process which is called the spinning. Now, another step is a transparent plate with selective opaque region. You see in between there is a mask, it is also called a mask, and there is a opaque region called a mask is then brought in close to the proximity of the wafer. Now, it will be put on the wafer. Now, on the region of the photoresist that may contact with the UV light. You see on the screen here that here is a contact mask we are using, and after that UV light exposes the photoresist. Now, we are having the photoresist developed leaving the window to SiO2. You can see on the screen that here we are having the structure developed on the wafer, and it is not developed where we are having a photoresist. Now, the result is a window through the resist to the SiO2. This exposed region is then chemically etched with the buffered hydrofluoric, that is HF acid, and the presence of the photoresist on the certain region, however, protects the SiO2 beneath it from being the etched. So, SiO2 chemically etched. Another chemical process, the remaining photoresist is stripped from the wafer leaving the patterned SiO2. Now, the substrate itself is now etched using a potassium hydroxide, that is a KOH solution. Unlike the previous etching process, however, the KOH-Si reaction proceeds at different rates in the different spatial direction due to the crystalline structure of the silicon substrate and its orientation. Now, you see that here is the photoresist stripped and Si and isotropically etched. Such a direction happened etching process is known as the anisotropic etching. Now, the finally conclusion we have you see here we have a silicon wafer, SiO2 layer grown, then photoresist put on, then the mask opaque region we are having. Now, after that, in the next step we are having the UV light exposed photoresist, then the photoresist developed leaving the window to SiO2. After that, we do SiO2 chemically etched, then photoresist stripped as Si and an isotropically etched. Now, this is the bulk micro machining. The substrate itself become the part of the structure of the MEM device. In this method, as we can develop a MEM devices. So, another technique we will discuss in the another lecture. Thank you very much.